Programmable logic arrays are systematic circuits that can be developed from Boolean algebra expressions systematically through software. These can be especially useful when developing more complicated circuits in LogicWorks or other digital schematic capture programs. So what are programmable logic arrays, or PLAs? They're a standardized structure to build a sum of products expression, and by using a systematic method, you can convert the Boolean expression into a network of logic gates. Since we can write software to build a PLA, it can be very, very quick to build a circuit. So why PLAs? Very useful for building complex control structures quickly. Very useful for complex control structures such as CPUs or adder units or things of that nature. PLA chips were available for fast SOP implementation until the 1970s, and PLAs were the fastest implementation method for integrated circuits until about the 1990s. Programmable logic has evolved more recently, though, since we now see more advanced synthesis, placement, and routing software used to develop and implement control structures, and more advanced programmable logic devices now exist, such as FPGAs and CPLDs. PLAs are still useful for digital schematic capture in LogicWorks, so we'll review them here. So PLAs in LogicWorks. One fact that you must consider is that there are no variable names such as A, B, C, F, G, H, T, U, V, X, Y, Z, etc. No variable names. Instead, variables are represented by bit numbers. Bit 0, bit 1, bit 2, bit 3, etc. PLA codes are used to represent these terms. So what is a term? What is a PLA code? Well, let's take a look here. Let's say we have a Boolean expression f equals a, b prime, or c. We have a term here, and we have a term here. PLA codes consist of a set of bits, which can be, or don't cares, which can be 0, 1, or X. The 0 is for inverted variables. The 1 is for non-inverted variables. And the X is for don't cares. So here's an example PLA that we can develop from the Boolean expression H. So let's break it down into its terms. Let's start with A, B prime, C. How many variables do we have first? A, B, C, D, E, F. We have 6 variables. So we have input bits 0, 5, 0 to 5. Let's keep this in mind. So our input bits, the most significant bit will be 5, 4, 3, 2, 1, and 0. So this will be bit A, 4 will be bit B, bit 3 will be C, bit 2 will be D, bit 1 will be E, and bit 0 will be F. Our output function is H. Output is how many bits? Well, we have only one output, H, so we will have output bit 0 as H. Looking here at this first term, A, B, and C. A is 1, B is inverted, so 0, C is not inverted, so 1, D for this first term here is a don't care. So we say X. E is a don't care again, so we have an X. And F is also a don't care because we don't see it in this term. So for this term here, our code is 101XXX. Let's clean this up here so it's a little bit easier to see. Let's look at this next term, A C prime E. Our code for A C prime E, well, A is not inverted, so we have a 1. B is not included. We don't care what B is, so we place an X. C is inverted. C must be 0. 0 inverted is 1, so 1 ended with E. When E is not inverted, or it needs to be a 1 again. D and F are both don't cares, so A, B, C, D is a don't care. E is not inverting, so we place a 1, and F is a don't care because we don't see it. So this is the code for A C prime E. Now we need a code for another term. The next code will be for B and D. A is a don't care. B is not inverting, so 1. C is a don't care. D is not inverting, so 1. E is a don't care because we don't see it. F is a don't care because we don't see it again. Finally, for the last midterm that we have, we need a code for C F prime. A is not included, so we have a don't care. B is a don't care again. C is not inverting, so 1. D, not included, don't care. E, not included, don't care. F is inverted, so 0. Let us list the actual terms for each of these codes. We have A, B prime, C for this first code. A, C prime, E for the second code. B, D is the term that is represented by the third code. And then C, F prime, which is represented by the fourth code. Let us try now to implement a LogicWorks PLA from this expression. First of all, go to LogicWorks and let's try implementing our Boolean expression directly. So we have 6 input variables. Let's create them. And let's label our input variables. We have A, B, and we have C, D, E, F. This covers all our input variables. Now we need 1, 2, 3 input ands. Let's place those. Oh, before that, let's look at the inversions. B prime, C prime, F prime. So 3 inverters. 3 NOT gates. 1, 2, and 3. Let's now place our inverted variables. like so. And we can label our inverting variables. B prime, C prime, F prime. So we can connect to B prime, C prime, and F prime. So let's go back and we see 1, 2 terms that have 3 inputs. So it's 2 3-input ANDs, 1 and 2. And we need 1, 2, 2-input AND gates here. And our first term is A, B prime, C. A, B prime, C. Our second term is A, C prime, E. A, C prime, E, like so. Our third term is BD, B ANDed with D. Our fourth term is C, oops, we have a incorrect connection here. Let's redo that. C, F prime. Finally, we need a 4-input, 1, 2, 3, 4-input OR gate to bring this together. So we'll connect here, and we have our Boolean expression. So we'll include a binary probe here, and we have our benchmark case. Oops, let's include some binary switches. And let's just label these for a virtual connection. We'll have A, B, C, and D. So now that we've implemented our Boolean expression directly in logic gates, we can test it using the binary switches. Oops, if C is 1, then we have an X. Where is our missed connection? It is, oh, right here, F. We need 2 more binary switches. Do apologize. E and F. Let's label those. E and F. Now that we have our binary switches, we can go ahead and play with this to simulate. So we had to place 1, 2, 3, 4, 5, 6, 7, 8 logic gates, and we had to develop the lines for the input lines for the B prime, C prime, and F prime variables. However, if we use a PLA, it is possible to generate a part immediately without having to go through the process of laying out our digital logic gates and then creating a separate part. Let's try creating a PLA. Simulation, go to the simulation menu at the top, And now we need to come down to this option, Prom RAM PLA Wizard. Let's click on this. We wish to create a new device, and we have a PLA selected. Click Next. And for the PLA data entry method, we wish to enter product term data manually. So we'll click Next. How many input lines do we have? If we use the pull-down menu, we have 1, 2, 4, 8, 10. We have actually 6 input variables, but the number of input lines is limited here. You can actually use the keyboard to use backspace and enter the number 6. You can enter any number of input lines that you like. Also, since we have only one output variable h, we can set the output lines to 1. If we have more than one variable, h, I, j, k, etc., then you can enter the number of output variables. You can use the pull-down menu, or you can enter something that is not on the list manually using the keyboard. We're going to leave the number of output lines at 1 because we have only one output variable, and just leave it at active high for now. So the product terms now need to be entered. Enter product terms for bit 0. Bit 0 refers to the output bit 0. So we're talking about output H. What are the product terms for bit 0? What are the codes for bit 0? What are the codes for H? Well, we have code 101XXX. Enter. This covers A, B prime, C. Next we have 1x, 0x, 1x. This covers the term A, C prime, E. Enter. For BD we have x1, x1, xx. x1, x1, xx. For our last product term we have xx, 1x, x0. 1x, x0. Now that we have entered our fourth product term, do not enter do not press the enter key of last time or the return key of final time. If you go to the next line, this corresponds in some versions of LogicWorks to all x's, so the output will always be 1 for h, and you don't want this. You want to have your last line include this code here. This should be your last line. You should not press enter after it. So our output type is active high. And now we can click next again. So we can open a library or create a new library. I'm going to go to a library that I created that corresponds to this series of lectures, which is called FirstLib. You can create your own library. And now that it's created, I can enter a name for this part. I can call this my PLA1. Generally, you would want to give it something more descriptive, such as 1-bit adder or 4-bit adder or 3-bit decoder, things like that. But this is just for demonstration purposes. Click Finish. And if I come now to the list of libraries, I can come down to firstlib.clf, and I see my PLA has been generated. It has in0, in1, in2, in3, in4, and in5 for 6 variables, and it has one output bit, one output variable. Let's bring this here into our circuit. In0 corresponds to F. So if we look back at what we declared earlier, 0 for F, 1 for E, 2 for D, 3 for C, 4 for B, 5 for A. And output 0 was for H. So in0 corresponds to F, in1 corresponds to E, in 2 corresponds to D, in 3 corresponds to C, in 4 to B, and in 5 connects to A. Finally, we can attach a binary probe to the output of our PLA. Now let's view it completely. And we can verify by comparing the output of this direct digital circuit that we generated that the PLA is correct. Let's compare a few values. So when B is 1 and D is 1. So when B is 1 and D is 1. Let's bring this high. B is 1 and D is 1. So regardless of any values of A, C, and E, we should not see it change. So we can bring down all these cases, and we can look at A, B prime, C, A, B prime, C, and we see both of them are 1 again. Both go to 0. C and F prime. So when F prime goes to F, it goes to 0, and then we get 1 again, and we see that the digital circuit that we directly implemented gives the same result as the PLA. Let's try an example PLA with multiple functions now. So we have U, V, and W as our outputs. So we have 3 output bits. We'll call this here bit 2, bit 1, and bit 0 for U, V, and W. 2, 1, 0, U, V, W. You can change the order, just remember to be consistent with your circuits. Now, what input variables do we have? We have A, B, C that are available, so that's 3 bits. 2, 1, 0, A, B, C. These are inputs, and these are outputs. So you need your codes to be the same width as the number of input variables that you have. So we have 3 input variables. Our codes are going to be 3 bits long. So for U, bit 2, we have A prime, B prime, C. Let's look at this. That's 0, 0, 1. We have A, B prime, C prime, 1, 0, 0. And then we have for the third, A, B, C, 1, 1, 1. For output V, output bit 1, let's look over here. We have A, B prime. A is 1, B is 0, C is X. For AC, A is 1, B is X, C is 1. For output W now, this is bit 0, output bit 0, AC, 1, X, 1, A prime, B prime, C prime, 0, 0, 0. So we have 3 sets of PLA codes. we can combine all three of these functions into a single PLA. Let's do this now. Let's create a new circuit and go to Simulation, and then we can go to PROM/RAM PLA Wizard to create a new PLA. PLA is already selected. Enter product term data manually. Input lines. Well, let's take a look. Inputs, we have 3 inputs. 0, 1, 2, 3 inputs possible. So we will come here and delete the 6 and enter 3. How many output lines? When we do a pull down, do the pull down menu, we have 1, 2, 4, and 8 as possible numbers of outputs. But when we look here, we have only 1, 2, 3 output bits. So we should enter that manually. Backspace, 3. Default output polarity should be active high. So leave it as is. Product terms for bit 0. What are the product terms? 1x1, 0, 0, 0. This covers bit 0. 1x1, enter, 0, 0, 0. Do not press enter after the last PLA code. This can cause a bug to occur in some versions of LogicWorks. Output type is still active high. Next, enter product terms for bit 1. V is bit 1, 10x, 1x1. 10x, 1x1. Active high, and we will click Next. Now for bit 2. 001, 100, 111. Bit 2 is listed here. 001, 100, 111. Let's verify. 001, 100, 111. Output type is still active high, so let's click Next. And we have now covered all of the output pins. So we have a library already called firstlib.clf. I am going to call this multi PLA 2. Finish. And now I can go to firstlib and I can bring multi PLA 2 out. Place it here. And now we can place our 3 input variables, A, B, and C. And now here's the question. Do we need to place any inverters for a PLA? The answer is no, because the inversions that we would need are already generated by the PLA code. So, in 0 corresponds to what? Let's look back here. C is input 0, B is input 1, A is input 2. C in 1, B in 2, A. Let's go to Simulation IO and place some binary probes. Let's place 3 of these. 1, 2, 3. Output 2, output 1, output 0. Place a few switches here. Just a note, if you tried clicking on this and you wanted to copy and paste it, you would need to shift click to copy and paste. So we'll connect the input variables so we aren't getting X's at the output. Now we can label each of these outputs here, output 2, output 1, and output 0. They correspond to U, V, and W respectively. So let's label these. U, V, W. So the nice thing about labeling these here, it gives us a little bit of clarity as to what the output variables are. And we can see what the final binary values are. And because we have only 3 variables, it's easy to go through all possible input combinations in this video without burdening you with TDM. So let's just go through here. 0, 0, 0. So you can see the output 0, 0, 1. Output is 1, 0, 0. Output is 0, 0, 0. Output is 0, 0, 0. Output is 1, 1, 0. Output is 0, 1, 1. Output is 0, 0, 0. And finally, output 1, 1, 1. So when you go through and you use PLA codes, it's possible to generate fairly complicated digital circuits and then contain them in a part with ease. This would necessitate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 logic gates. You would need to place 14 logic gates and then several input ports, 3 input ports, 3 output ports, and connect them all together properly. And since we know, based on the Boolean expressions, how they look, we can just enter codes corresponding to these Boolean expressions and generate the part instantaneously, hence saving time.